Okay, so I'm going to solve the following problem. We're going to look at the Fourier, sorry, not the Fourier transform. We'll get there, but the partial derivative of u with respect to t is equal to the double x derivative of u, and then minus gamma times the x derivative of u. And we're going to assume that u of x0 is equal to some given function f of x. This is very similar to a homework problem question. There's a sort of a, not a typo, I'll say, but the standard way to write the corresponding, so if you haven't looked at the homework yet, you'll see very clearly that this is similar to a homework question. The standard way to write that is with a minus sign. I put a plus sign in the homework just because, I don't know, I wasn't thinking, I guess, or something when I made the homework assignment. It doesn't matter in terms of the math. Okay, you're still gonna be able to solve it, and just, if you want to use my reasoning here and follow along, just wherever I write a gamma, imagine it's a minus c or something like that. But what's happening here, and there's already some good discussion about this, which I really appreciate. What's happening here is this is called a diffusion. A diffusion equation. Sorry, diffusion. Convection equation. Diffusion convection equation. And what's happening is this part right here, the double x derivative of u represents diffusion, and this derivative right here, or this term, the minus gamma partial x derivative of u, represents like the entire system moving. So one thing this would model would be, let's say you have a river that's moving at a constant rate, and you have some pollution here, and as the river is flowing, the pollution is spreading out, but it's also flowing like this. So there's sort of this process, this diffusion convection process. It's diffusing, and it's also moving as it goes. Okay, sorry, I just wanted to make sure I was in the frame. Okay, and I'll talk some more about that physics a little bit later, and how we can actually use that physics, or that sort of, what this is modeling, to actually come up with a solution to this equation. But for now, just to get some practice, and because it doesn't always work, just to get some practice using Fourier transforms, I'm going to solve this using Fourier transforms. So first, I'm going to take Fourier transforms of both sides, and when I do that, I'm going to get the the t derivative of the Fourier transform of omega t on the left-hand side. And on the right-hand side, we're going to get minus omega squared times the Fourier transform. And then remember, this part is going to be minus gamma. Let me write it like this. Minus gamma I omega times the Fourier transform of u. I can combine this left-hand side or the right-hand side into one term, and this is going to be equal to minus omega squared plus I gamma omega u hat of omega t. All right, now this is an ordinary, if I think about omega as being fixed, this is an ordinary differential equation in the t variable, and so the conclusion is that u hat of omega t is going to equal u hat of omega 0, and then times e to the minus omega squared plus I gamma omega t. Now u hat of omega 0, that's just f hat of omega. So this is the Fourier transform of the initial value. So this is f hat of omega. And I'm going to split this up into a product. So this is e to the minus omega squared t. And then we're going to have e to the minus I gamma omega t. Now, we've already seen, we know what the inverse Fourier transform of this is. Okay, let me write that over here. That's just, this right here, remember, this is exactly what we got when we were looking at the diffusion equation. So the inverse Fourier transform of f hat of omega e to the minus omega squared t is 1 over the square root of 4 pi t times the integral y going from 0, sorry, not from 0, from minus infinity to positive infinity. That's a y. This is a y integral, y going from minus infinity to positive infinity, f of y e to the minus x minus y squared over 4t dy. Okay, so why is that important? It might not seem completely relevant now because we have now a product of 3 terms, not a product of 2 terms. What we're going to do, I'm going to do some computations down here and then erase it. I'm going to look at this right here. So I want to look at the following scenario. So assume we're looking at the inverse Fourier transform, because that's what we want to do. We want to find the inverse Fourier transform of this times that, where we already know the inverse Fourier transform of this piece. So we're going to look at 1 over the square root of 2 pi, and we're going to have omega going from minus infinity to positive infinity, g hat of omega times e to the minus I gamma omega t e to the I omega t d omega. And just to make it clear, what I'm saying here is we're going to compute this, and we're going to apply it to where, this, of course, is going to correspond to this portion. And this g, this might be the confusing part, this is going to correspond to that right there. Okay, so when I do this computation, well, what I'm going to do, because I'm going to run out of, well, maybe I won't run out of room. I'll just not be lazy and rewrite everything. So now we're going to look at the integral, not y, omega equals minus infinity to positive infinity. We're going to have g hat of omega, and I'm going to combine this into one exponent, and so we're going to have I omega, and then it's going to be times omega t. Wait, sorry, there's a mistake here. I'm doing it in the x variable, so that should have been omega x. I wrote omega t. Sorry about that. Okay, too many variables. All right, and so this is going to be x minus gamma t d omega. I've got I omega and then minus gamma t. That's why I have that there. Okay, well, what is this? This is just the inverse Fourier transform of g hat, but evaluated at x minus gamma t instead of x plus, or instead of x. So what this tells us then, I'm going to write it in a different color so you can sort of distinguish it, hopefully. The inverse Fourier transform of g hat of omega times e to the minus I gamma omega t is g of x minus omega t. That's what we have there. X minus, gamma t. X minus gamma t. That's what this says over here, is the inverse Fourier transform of g, but we are evaluating it at x minus gamma t. Okay, so I'm going to erase all of this purple stuff and the arrows. So either pause it or something. If you want it, write it down. I'm about to erase it. Okay, so then we're going to combine these two rules here. Okay, I want to know the inverse Fourier transform of this whole thing. I know the inverse Fourier transform of that. So the inverse Fourier transform of this whole thing is just going to be this function, but instead of evaluating it at x, I'm going to evaluate it at x minus gamma t. And the inverse Fourier transform is the solution. And so what this tells us is that u of xt is going to be equal to 1 over the square root of 4 pi t. I'm going to have the integral y equals minus infinity to positive infinity f of y. Now wherever I see an x, instead of writing an x, I'm going to write x minus gamma t. This is e to the minus x minus gamma t minus y squared over 4t dt. And this should, if you think about what this x minus gamma t does in the space variables, this should be very consistent with your idea and with our the fact that this is modeling a diffusion equation that is spreading, or that is moving. The diffusion process is moving. The x minus gamma t is very consistent with that, and I will talk a little bit more about this in the next video.